Okay, let's start. Do you have any questions? All right. So let us maybe just say a few things again about the 6.3, right? Let me see. 6.6, no, 6.8, I think. 6.7. Okay. So it's the joint, let's say density, right, of functions of random variables, right? So the point is that if you have a vector, right, and you map it to another vector, right? And you can call this whatever you want, yn, for example, y1 to yn. Okay. Then the density, right, of the new variables, let's say, right, is simply the density of the old variables, right? Now, so what the textbook will do is they'll just write this, right? And then let me just write that, okay? So that's what the textbook would write. But what it really means is that you take the original structure, right, of the density of the joint densities, but you have to solve, right, for the x in terms of the y variables. And this determinant, right, which is the partial of the g function, must also be solved in terms of y, right? So, and so the inverse here is just reciprocal because determinant is already one, determinant is already a scalar, right? So all this is in terms of y, right? And j here, right, is the partial gi over partial xj, right, for ij, right? This is the J matrix, okay? So, yeah. So basically, it's really just a formula. If you want to ask where the formula comes from, right? Or let's say the proof, we won't really prove it here, but if you want a proof of the formula, it's really just, either you can look at a change of variable, U sub, or chain rule. But of course, we're looking at the multidimensional version. So it's along this topic. And you can consult, Calc 1, Calc 3, right, for the reason why it works that way. But in this should not be the first time, right, you encounter determinant of Jacobian. In Calc 3, right, this is what you use quite often, I guess, or at least part of the, one of those chapters, right, that you have to do change of variable for multiple integrals, and that's what you use, right? But we won't really go into that here. But what I want to emphasize, right, are the points or so here the formula should be used if you have more than one variable because the CDF is not easy to be written down, right? From beginning to end, like from scratch without, invoking the formula. But so maybe let me just say some points to pay attention to, right? So the first thing is, again, right, you have to solve for whatever name it is, right? Sometimes you go xy to uv, x1, x2 to y1, y2, whatever, right? So, but in this context, you have to solve for the old variables, right, in terms of new variables. Let's just put it that way, right? So you have to solve for x1, xn in terms of this will almost always be there. Maybe you don't have to solve it completely. Okay, you may, for example, you may see that in your substitution, right? If you have something like this, suppose that xy, right, you map to x plus y and x minus y, right? And suppose that somehow the Jacobian is 1 over x plus y. And suppose that somehow your joint CDF, right, is e to the minus, let's say, lambda x minus y. I don't know. I'm making this up. I don't think there's such a thing, but I'm just making it, all right? This should not be a PDF. But if that's the case, then clearly, right, you already kind of see that this is 1 over, and this is uv, right? So this is 1 over u, and this is e to the minus lambda, right, times v, right? So you do not, so usually you solve for the old variables in terms of a new variable so that you can plug it in and express everything in terms of new variables. But if it's already convenient, then you don't need to do that, right? So that's the first thing you want to kind of like see. But more than that though, right? There's another reason why you do this. The reason is because you have to pay attention to the range of values of the new variable. All right. And this is most often missed in the formula because the formula doesn't really say, right, range of values. This part is missed, or not missed, is not stated for good reason because, there's no formula you can write down. And in general, right, I'll tell you one thing that not much you can write down, but there's something you can follow. For example, right, let's take a look at um 6.60 part A, where you have xy as independent uniform 0, 1. So the range of values of xy, right, is 0 to 1. And then you have u is x plus y, v is x over y, all right? And so here, you do your Jacobian and all that good stuff. That's fine. But what about range of values? right? And again, without the range of values, okay? Let's say without the range of values. Let me say, maybe you get half credit or so. This might seem harsh or whatever, right? Because after all, isn't the formula here? The answer is not really. The formula is not a formula without the range of values. Because, right, for example, we'll discuss it. But you might have something like this, right? That, for example, you might have f of uv is, let's say, 1 over u square times, let's say, 1 over 2v, which looks super cool because that seems like they're independent. And if you only have this, you might as well say u and v are independent. But until you look at the range of values, and if you find it out correctly, you might have something like this. Again, I'm making things up because, right, they may not be a proper density. But what I'm trying to demonstrate is that, right, without the range of values, you may make the wrong conclusion about the nature of the interaction of the random variables. Okay, so the range of values is crucial for the density. Okay, in fact, I mean, you'll see that the range of values play a very important role when you do statistics. Okay, on the parameters of the distribution. But let's go back to this example, right? Here, if you look at the range of value of u and v, well, clearly u is between 0 and 2, right? But what about v? Well, you may be tempted to say that, right, a number between 0 and 1 divided by a number between 0 and 1, you really get a number between 0 and 30. And while that's not wrong on paper, it's wrong in practice here. I mean, again, it's not wrong, but it's not enough. The reason is actually that's not enough because u and v here have some interaction because they're both made up from x and y between 0 and 1. You understand? So the range of values is something that you can only do, let's say, properly if you backtrack it to the original variables. How? So basically, right, here you have to solve for x and y in terms of u and v. Looks a bit painful, right? But if you kind of, play around a little bit, you see that u times v, right, will be what? X squared over y plus x, right? Which is x times x over y plus 1, which is v plus 1, right? So x is uv over v plus 1, right? Similarly, if you divide u over v, you get y over x, right? So y plus y squared over x, which is y times 1 plus y over x, which is y. Wait, am I right? Yeah, right. Y times 1 plus 1 over v, right? So therefore, you know what? Do I need this? Well, I can just subtract u away from this, right? U minus this is v, whatever. So then y, right, is u over v divided by 1 plus 1 over v, right? If I multiply v across, do I get u over v plus 1, right? All right. Yeah, of course, because, if you have u times v here, right, which is x, if you multiply by y over x, then you get y, right? But y over x is 1 over v. So, yeah. Okay. Anyway, so the point is what? The point is then after you do this, then because x and y are naturally between 0 and 1, then the range of values for u and v are such that, right, uv over v plus 1 is between 0 and 1, and u over v plus 1 is between 0 and 1. That's the correct range of value. Now, is this, how to say, useful when you work with u and v? Maybe not. Maybe you have to work out more, right, of what that means, what this means. But provisionally, this is what you have to do, right? For example, you see that the one of the interaction between u and v is what? U is less than or equal to v plus 1. From here, you see. And then, of course, right, there's some other interaction from this side. But if you do not back solve, right, for the all variables in terms of variables, most likely you get the range of values wrong, because it's not easy to read off the range, the interaction just from the new function. So the key is to solve back and then just plug in the old range of values. And you can leave it as that for now, unless you have to work with the random variables themselves. Any question?
So when we're backtracking, are we, like, for example, u times v and u divided by v, are they just arbitrary that they look to like they would work to simplify the process of backtracking, or was that like a specific one?
Say that again. I'm not sure I catch the question.
Like when we were doing u times v to isolate for x, and then we did u divided by v to isolate for y, were they just arbitrary like relations between u and v to isolate for x and y? Could we do like a different like u plus v?
No. Your question has to depend on what functions were given. And you have to play with this for a while until you see that what I'm doing here is natural. Because if you were to solve for x and y here, what combination would you do? U plus v would not get you anything nice, right, in terms of x and y. You know what I'm trying to say? I mean, not that you cannot do u plus v, but what u plus v is x plus y plus x over y, which is not helpful in terms of solving for x and y, right? I think.
I see. So just to confirm, like we use those functions that are like useful in terms of the functions that we were given.
It's basically just solving a system, period. Meaning, for example, if you have u equals to x plus y and v equals to x minus y, then of course, x is u plus v over 2, and and y is u minus v over 2. Right? So there's nothing magical about me using u times v. It's really just the solution to this system in terms of x and y. Right? But I don't know what the general formula is, because it depends on what the system is. It's a nonlinear system, and that's why it's a nonlinear solution. All right, any other question? All right. So that's the 2 points. The third point is not really about paying attention to, but it's sort of like one of the side effect, if you will, or one of the surprising reason why people do transformation, right? So, which is this what we're looking at here. So basically, this may be an, let me say, easy or easier way to find distribution of a random variable. All right. So what do I mean by this? So for example, if you have x and y, is given, right? Let's say, I don't know, it's the independent standard normal. All right. And then you're asked to find the density or distribution of, let's say, u equals to square root of x squared plus y squared. Let's say that's the question. Okay. Now, let me tell you that right off the bat, if you have no experience, or even with some experience, let's say like I am, and let's say you start working with the CDF, which is, commendable because that's what I tell you to do, it won't be easy. Why is it not easy? Because this is a function from two variables into one variable, right? So the CDF analysis would involve, it will involve a double integral. So I'm not so sure. It might be easy. Who knows? It might be easy. Who knows? Or it might be possible, right? You will integrate the double integral around a region here. Maybe I'm exaggerating, but let me tell you that maybe I'm not giving you a most convincing example, but in this case, it might be surprising to you that one possible way, so this involves a double integral, right? Which is easy or hard, I don't know. Let's just say involve a double integral. But one possible way to solve this is to actually, instead of solving for this only, is to get a pair. Let's say this. All right. And this is where it's most counterintuitive to some students, because isn't this more work and more formula than this, right? Because two is always harder than one, maybe. Who knows? But when we, as in like, I don't know, people with experience talk about difficult thing or not, it's really not about the amount of calculation, but just about the way that you can do it or not, right? Because if it's impossible, then it doesn't matter if it's one line or two lines, it's impossible. But what I'm trying to say is that when you open up to two variables, they might have some interesting interaction in terms of the Jacobian, etc. So that in the end, what you end up having is that u and v are independent. Or let me just say slits, right? So there are problems, there are examples of this around, right? Where solving for one variable, a single transformation is harder than solving for both transformations together, or a pair, and then just isolate what you want. And that's as best as I can tell you, right? I mean, maybe later on in your work, you will see some experience of this. But what I'm saying is this is not just a technique in the abstract where you make transformation here, transformation there, and you do whatever you need. But sometimes even if you want a single transformation, it might be surprising that finding the joint distribution with something else is the easy way to go. All right. So that's one point I want to make. And that's it. That's all I want to say about this this topic. All right. So now let's continue with 7.2, right? Which is the topic of expectation of a sum. And actually, in terms of the mathematics, there's not much to be said, right? Unlike this problem, there's kind of a bunch of calculation here. The only thing we need to say is expectation of a sum is a sum of expectation as long as it's finite. Doesn't matter, right, how the xi's behave. So independent or not, doesn't matter. Okay. So that's the beauty of it. The hard thing in terms of these kind of problems is for you to decide how to break down the original x, okay, in terms of suitable xi to calculate. So right here, right, basically you want to calculate the expectation of random variable. You break it down to components and then calculate, all right? So again, right, the hat problem cannot be overemphasized because it's sort of like the classical problem where this technique is used, right? Where if you want to let you look at the number of persons with the right hat, then the distribution of x itself is, let's say, tedious to write down. I mean, if you don't know how to do the number of people with no hat, right, with no the probability that no one gets their right hat, then you can't write down the distribution of x. But even if you can write down the distribution of x, writing expectation of, so let's say n people, right? Expectation of x as a sum, right, of k from 0 to n of k probability x equals to k is not the way to go, because this expression is quite complicated, right? The probability of exactly k people getting the right hat. Let's say it's not a pleasant thing to write down. It's not hard. It's just not pleasant to write down because it's, 1 minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial, blah, 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 right? Not pleasant. But if you break the x down into components where xi is 1, if the ith person gets the right hat, and 0 otherwise, right? And so far, actually, this technique is quite common. When you have something that reads as total, even though right here it might not say the word total like right out, but it is total, right? Total number of people getting the right hat. Then you just, total is a sum of individuals, right? That's how we count, by the way, right? We count by going through the cases, and if it works, we count it up by 1. If it doesn't work, we don't count it, meaning we count it up by 0, right? So it's supernatural when you think of it that way. It just gets a little bit, let's say, fancy when you write down in terms of symbols. But then expectation of x then is the sum then of expectation of xi. And you see the beauty of this is that, right, instead of analyzing the interaction of n people, because of the beauty for property of expectation to pass inside the sum, regardless of the interaction, it allows you to pass your attention into the component and then ignore the interaction. Variance requires you to look at the interaction, but two at a time, so it's still tolerable, right? So anyway, so here you just have to look at individual person. But individual persons clearly gets the right hat with probably 1/n each, right? So that's 1, right? It's 1 regardless of how many people you have. And here again, right? You should remember that a Bernoulli random variable, that takes value 1 and 0 under some event, right? This is the event. Then expectation of the random variable is exactly probability of the event, right, being successful. And of course, the event being successful here is the event that the ith person getting the right hat, which is 1/n, right? There's one chance that the person gets his hat out of n hats, right? Sorry, 1/n chance. Okay, so far, any question? Another example, which is maybe a little bit closer to what we have studied, is the hypergeometric problem. Hypergeometric random variable, right? So if you remember, the hypergeometric is what? The context of it, right? I just need to get my notation lined up like the textbook. So you have an urn, right? With 2 categories. M of them is white. N minus M is whatever other color, let's say black. And you take a sample, right, without replacement. Right, of size N. Right, you sample N, right? Out of the urn. And the random variable represents the number of white balls in the sample. So to remind you, right, that probably x equals to k. So k here, right, is between 0 and the minimum, right, of m and n. Because clearly you can have more white balls than whatever there is in the urn. You can also not have more white balls than whatever you sample right out of the urn. Will be the denominator, right, is n choose n, right? And so yeah, and then out of m whites you choose k whites, and then out of the remaining you choose the remaining, right, like that. And so I think, right, we said when we looked at this expression, which is expectation of x, that is let's say unpleasant to look at, right? And we just write out the answer. Okay, but does anyone remember what the answer is? The answer is very intuitive, right? The answer is the sample size, that the urn size, right? The population size, if you will, times the success probability. Sorry, sample size, of course. Sample size times the success probability. What success probability? Success probability is M/n, right? Which is exactly like the binomial. Which, right, is surprising because you see the difference, right? The key difference between the hypergeometric and the binomial is sampling with replacement or without replacement, right? If you're sampling with replacement, meaning every time you take a ball out, you replace it in, then this will be a binomial, NP, P being this. Agree? But this is not a binomial. So why is it this way? Maybe you should raise that question, right? Even though the answer is correct, you should raise the question. And the answer is what? How do we get to the answer? The answer is from the technique, this technique. How? I mean, okay, of course, the textbook, when we went over this sum, right? The discrete random variables did work out this sum in, let's say, a quite clever way, right? That, let's say, if you look at once, you may have no idea if you're trying to recall it, because, let's say the calculation is not super inspirational. But if you break this down into this, now let's see if you see the idea. What are the components here? What are we summing over? I should run from where to where? So X is the number of whites in the sample. It's the total number of whites in the sample. So you're just tallying up, you're counting over what? You're counting over the sample itself, right? You count over the sample, where this is each ball in the sample, and it will be 1, you count it up if the ith ball in the sample is white, and 0 otherwise. Notice exactly like the hat problem, right? The xi here certainly have interaction because it's sampling without replacement. However, when you look at the expectation, the rule of the expectation or the property of the expectation itself allows you to just go straight into the marginal and ignore the interaction. And this will be, right? You see each of the xi will be a white ball, right? Well, with exactly probably m over n. And again, right, some student might find this weird because doesn't the xi have interaction? Why is it m over n? The reason, again, is because when you look at expectation of xi, the meaning of it is that you just look at the ith ball regardless of the other results, or in the black, like in the dark, meaning that you do not know any other result. You're not watching the whole sample, you only watch the ith ball. And of course, as far as the ith ball is concerned, it can be white with probably m over n, because what else do you know, right? There are m balls that's white in the earth. So any ith ball is the same. Therefore, that's the answer. Any questions? All right, so let's do one more problem. That is, let's say, sort of like classical of these types. Maybe 2 more, okay? The first one is called let's make it a quiz, why not? This is called the coupon collecting problem. By the way, if you ever take Math 478 and using, let's say, our textbook, depends on who teach it, but I always like to emphasize coupon collecting problem because this technique is quite important in 478. And there are tons of coupon collecting problem, not just one, but this is one of them. So this is like this. Suppose there are n types of coupon. And each time one obtains a coupon, it's equally likely to be any of the n types. Fine. So let X be the number of coupons needed to get a complete collection. Find expectation of X. All right. So the first time you see this kind of question, maybe it's even hard to understand what they're referring to. And at least the language of coupon, let's say withdraws, just really means that something that has so many types. One easy way and exactly describing this type of problem, you can think of it as rolling a dice. Not necessarily a 6-face dice. Just think of it as n-face dice, but 6-face is fine. Let's say a 6-face dice. Well, if that's the dice, and it's just a dice, right? So this is when n equals to 6. All right. And so each type you see is just the face. So the question really is this, right? If you roll a dice, it can be a number, but the number can repeat, right? For example, 1, 2, 1, 1, 3, 1, 2, whatever. But after a while, you will see all 6, right? Maybe like that. Then that's exactly the first time you see all 6. That's a complete collection. And that's a random number, right? That's a random variable. Okay. And you want to find its average, its expectation. So we understand the random variable and what it's doing, right? Now, once again, with this kind of problem, the old knowledge that you learned about distribution of a random variable is there in the background, but it's not going to be super helpful. The reason is, right, well, clearly you need at least 6 rows, right, to get all 6 types. That's clear, and you can write down probably x equal to 6 very quickly because you have to get 1 type each. Maybe not quickly, but let's say you can write down. But you see that here, x can take any values from 6 to infinity, right? And let's say you want to write down x is equal to 100. It's going to be a very painful process, and I don't even know if I can write down yet. Why so? Because you have to account for all possibilities, right, of repetition of the 6 types, and it can repeat so many ways. Basically, I think when you look at this thing, it will involve, right, a study in combinatorics that asks you for a integer solution, right? Integer solution equation. You sum 6 variables up equals to 100. How many ways can you get integer solution, right? When you sum 6 variables up and it equals to 100, right? Because that's exactly the number of ways. No times this repeat. And then who knows something else. So that's a, let's say a combinatorics, I don't want to call it nightmare, but at least for someone who's not trained, combinatorics might be a nightmare, who knows. But the point is, right, you're not really asking for the distribution of the random variable, you're asking for its expectation. And that's the beauty of probability, because there are ways around the question without directly addressing the distribution, which is, again, right, breaking the random variable down into components. So what component? What are the xi? And how are we summing it up to get to the total number needed to collect? So you see here, right? It probably will take you a little bit of time to think about it, but you just look at the collection process and what do you have? First coupon, you will all immediately have the first type, right? It may not be 1, it can be 6, right? But that's the first type. And then, right, it may repeat for a while, who knows? And then you will collect the second type. And then these might repeat among themselves until you collect the third type, right? But the crucial, let's say, moments is the moment you collect the first coupon, the moment you collect the first type, second type, and then third type. And basically, right, in between is the wait time, right, to obtain a new type. So in other words, this is going to be sum from 1 to n, where xi is the number of coupons needed to obtain a new type after having obtained I minus 1 types in a collection. Do you understand? Right. So x1 is the number of coupons needed to obtain a new type after you have no type in the collection. So therefore, for example, x1 is 1. But x2, right, will be a proper random variable. Right? What is x2? What kind of distribution is x2? x2 is the number of coupons needed to obtain a new type after having obtained 1 type in the collection. You already have 1 type in the collection, and there are n types total. So how many coupons do you need to collect before you have a new type? Well, x2 will be a geometric random variable, you see, because you're waiting on a success, right? Success being getting a new coupon, right? So what's the success rate? The success rate is n minus 1 over n, right? Because any of the remaining n minus 1 will be a success for you. You understand? X3 is geometric, n minus 2, right, etc. So xi is geometric, n minus I minus 1. N minus I plus 1, right? Like that. Agree? So then, right, expectation of x then, the total number is just the sum of expectation of xi. But if xi is geometric like this, then expectation of geometric is 1 over p, right? What is this p? So it's just really the sum of n over n minus I minus 1. And if you really try to write down, for example, right, when I equals to 1, that's n. When I equals to 2, that's n over n minus 1, right? And then n over n minus 2, etc. And then the last one will be I equals to n, right? N minus 1. N minus 1 is 1. So, hold on. Wait. Sorry, I apologize. When I equals to 1, that's 1. Right? And then the last item is n. Any question? All right. I guess one last question then. This is also, last question, last example, whatever. This is also it can be a coupon collecting problem, but let's see here. This is, so it says this 10 hunters are waiting for ducks to fly by. So the hunters fire at the same time, but choose the target randomly, independent of each other. Now, each hunter independently hits the target with probability P. Okay. So there are 10 hunters, but then they also say there are 10 ducks. Find the expected number of ducks that escape unhurt. With a flock of 10 birds. 10 ducks. All right, are we clear on the problem? So there are 10 hunters, right? It's some sort of like flipping a coin somewhere here, right? But basically for 10 targets here, each of them choose the target independently. So first of all, right, there's a possibility that 2 of the hunter here choose the same target, or there's a possibility that 10 hunters here choose the same target, right? And then if they choose the target randomly, right? Then each of them hit the target with probability P. All right. And then, well, you want to ask among the targets, how many gets no hit? Which, right, I guess involves 2 possibilities. Either they got shot at, but they missed, or they did not get shot at all, whatever, right? But we want to find the average number that does that. Again, right, you see, if you just think of the distribution, it gets probably complicated, right? Because we have to consider many scenarios. But that's not what we're involved with here, right? We just want to find expectation. So let X be the number of ducks that escape unhurt. Let's just say escape, right? And you see, well, the theme of this section is you want to write this as a sum. But we're summing over what?
Perhaps we can sum over number of hunters who make the
No, right? Because you will get double sums and stuff like that there. If you sum of the hunters, you see the hunters could aim at the same bird, right? Which means if you count success that this hunter missed the bird or whatever, you see what I'm trying to say? So no, I think it's pretty straightforward to sum over the ducks, right? Because it will be 1 if duck I, the ith duck, escape unhurt. Agree? So we should focus on a duck rather than a hunter. Okay. So expectation of X will be sum of expectation of Xi. And we just need to find expectation of Xi. And it's pretty clear, right? That all the Xi have the same expectation because symmetry. So we just have to find 1. Sorry, 1 to 10, right? But what is it? So actually, right, you see here the both number of 10s makes it confusing. Not confusing, but it could be confused between hunters and ducks, right? We should switch we should have the numbers differently so that we can distinguish. But suppose you have 8 ducks here, this is 8. Okay. So what's the expectation of the duck? Well, what's expectation xi, which is the probability, right? The bird I escape unhurt, which is what?
One minus P.
No, this is only for one hunter. Right? Remember, there are 10 hunters, which may or may not aim at it. So independently, right? So what is it? So each hunter, right, choose their target independently with probability P, right? So let's see here. So the hunter, sorry, each hunter choose their target randomly. So the probability that hunter, oh, what I'm trying to say is this. So it should be, right, that I want to say, yeah. So it's this. So let's just look at it like this. So okay, let's write down. Expectation of xi is probability, right, that the ith bird escapes, right? Now, which means that, let's say, first of all, it's going to be the probability that the ith bird, the ith duck, escapes, right? Let's say from hunter K, right? For K runs from 1 to 10, right? Because it has to escape from all hunter. And because all hunter acts independently of each other, right? It will be product, right? K from 1 to 10. Okay, so far. So basically, we just need to analyze the action of the ith duck from the hunter K and then multiply them all together. And in fact, right, it should all be the same with all hunters, so it will be raised to a 10 power anyway. But that's sort of what it is, right? So the product because of independence of the hunters. And so now, what is the probability that ith duck escapes from hunter K? Well, how does hunter K look at the ith duck? Two things, right? He would choose the ith duck first and then shoot it. Agree? So let's say this is product K from 1 to 10 of 1 minus, notice the 1 here is in the product is probability that the hunter K hits, right, the ith duck. Yes. And that's probably where you get the 1 minus P from. But the first thing is that it's the action of all 10 hunters. But the second thing, right, is that the hunter P does not just hit at the ith duct. He has to choose the ith duct first. And he choose the target. This is right, randomly here is the word for what? Code word in this textbook for uniformly, right? So meaning that the hunter K would choose the ith duct with probability 1/10. Agree? So if you want to analyze the action down, hunter K chooses, right, or aim at, right, right, and then probability of hunter K hits. I guess you can condition on aim at the ith duct, but that's sort of like imply. And this is multiply. Do you understand? And so, right, hunter K will aim at the ith duct with probably 1/10 because he chooses a target randomly, meaning uniformly over the ducts. And then, right, of course, the hitting probability is P. So the final answer here is 1 minus P/10 raised to 10 power. Right? But that's just expectation of xi. So expectation of x is the sum of expectation of xi, I from 1 to 10, which is, they're all the same numbers, so you just have a 10 in front. Any question? So I think, right, this part right here about analyzing the action of the hunter is sort of like the crux, probably summing over the bird as well, summing over the duck as well. But right, so that's that. Any question? Now, let's try to see if you understand the problem, or at least understand the solution. What if I change the numbers of ducks and the number of hunters to be different, right? Because I think somehow the 10 and 10 here doesn't help. It sort of hides, right? Repeat the problem. Let's say with M hunters and N ducks. Everything else the same. What should the answer be?
N times 10 minus P over N to the power of M.
Nancy, 1 minus P over Nancy raised to Mike. Is that right?
Yeah.
So as you said?
Yeah.
That's correct. Yes, right? That's correct. Because the over end here, because the hunter chooses over all the ducks. So the end here, right, is over the duck. That's correct. Raised to M power here is correct because you have to look at the action of all the hunters. And then the end here is correct because you're summing over the ducks again. That's correct. Good. All right. So like that. Any question? All right. So let us continue. 7.3, we'll skip. Let's move on to 7.4. Let's talk about variance, our sum of random variables. Along the way, right, the relevant topic will be covariance and correlation. Of, I guess, of a pair of random variables, right? So maybe first let's define covariance. So covariance of X and Y sort of capture the interaction of X and Y, but only in some specific way, right? It doesn't capture everything. It has been shown that the covariance as we defined here, which is related to what's called a Pearson correlation, sort of is related to the linear relationship between X and Y more than anything else. But that's some advanced topic for you. But just think of, just remember, if you will, that covariance as we define it here doesn't have to be the way to measure the interaction. There's other ways. So here will be expectation of, let's say, X minus expectation of X times Y minus expectation of Y. Okay. Which you see, if you expand it, will be expectation of X times Y minus expectation of X times expectation of Y. Okay. So that's covariance for you. It's just a definition. And again, I don't think there's a Pearson covariance, but there's a Pearson correlation. So it's basically related to that, related to linear regression and all that stuff. So what properties of covariance you should know? Well, surprisingly, I think students may not recognize the following property. The first one might be obvious. Variance is covariance of a random variable with itself, right? Again, very obvious, and I think students probably will recognize this right away, but it's worth it to show, right? To mention. The second one is actually the one that students don't usually know. It says that covariance is a bilinear operator. By it's just referred to the two dots here, meaning that it's linear in either positions, right? Either arguments. And if you think the word bilinear is strange, it's not. You have seen bilinear operator all your life. Product is bilinear. Inner product is bilinear. So it's just, oh, sorry, I guess I have one more thing to say, but maybe after this. So what that means is, for example, covariance of AX plus BYZ is A covariance of XZ plus B covariance of YZ. All right. And it's exactly this bilinear stuff that makes it very useful for you to calculate covariance of a sum. Because covariance of sum, you see, can be broken down into covariance of individual terms. Okay? And that's why covariance of a sum is not scary, because of the bilinear structure. And so notice this is linearity on this coordinate, right? On this argument. What about this part? So meaning I can write down the same equation with the switch, right? Which is obviously true because of the symmetry, right? What do you call it? Like, yes, just called symmetry, right? Covariance is symmetric, right? So I should have mentioned this first, and then this is obvious, but well, or obvious or not. So how do you prove this? Let's say, right? This needs to be proved. You see the proof, if you will, go straight into this expression. I mean, this will be actually not convenient to prove it. You can prove it here too, but you can see it more easily here. Why? Because the ax plus by, if you plug in here, then it will be linear with respect to expectation. And the product here, right, will be a constant with respect to this sum. You know what? Let me just show you. For example, right, covariance of ax plus by. Ouch. Z, right? If you chase the definition, will be ax plus by minus expectation of ax plus by, and then z minus expectation of z, right? Like that. So it looks scary and whatnot, but if you see the structure, what's happening, the first thing is, right, notice that I can distribute the ax plus by, right? The expectation inside it, ax plus by, meaning I will get something like this. A times x minus ex plus b times y minus ey, right? Times z minus ez. You see? Because expectation can go inside this. And then I will distribute this individually, which I will get. And then of course, right, the a here can come out, right? But well, maybe let me take one step. But now it is clear, right? That's a covariance of xz plus b covariance of y. Do you understand? Any question? In fact, right, covariance is not just like in a product. It is to some extent in a product. The in a product you learn in Calc 3, but there's some thing that prevents it from being in a product, which is the subtraction by ex here. If all random variables have mean 0, then it is like in a product. It is in a product. But this property right here is not really paid attention to by a lot of people. And it will allow you to look at some geometry of random variables via the structure of covariance in a nice way. And there's work done on that, not based on that sort of observation, right? I won't get into that, but just keep that in mind. It might be very helpful when you try to understand something, right? About interaction of random variables, especially when it comes to like something like multivariate normal. All right, so that's covariance for you. Now correlation. I don't know what the notation really is. Let me just call it COR. I don't know what people really call it. I think some people call it rho xy, maybe, who knows, right? Whatever you want to call it. Will be covariance, right? Definition divided by square root of variance of x times variance of y, right? Square root. And of course, square root, as we know it, right, is standard deviation, right? So I think sigma x, right? Sigma y is probably some notation people use, who knows? And so you might have seen something like this too, right? Covariance of xy is correlation, right? Times standard deviation, right? Whatever. So that's just definition. What do you need to know? about correlation. Well, I am willing to bet this is not the first time you see correlation definition. So, right, the only thing we need to remember is correlation is between -1 and 1, right? With 0 being uncorrelated, right? Or covariance being 0, but that doesn't mean, right, independence, right? Zero covariance does not imply independence. What else? Unlike covariance, correlation is not linear, okay? It's not bilinear. So in that sense, even correlation is very popular, right? It's not friendly in terms of computation. I repeat, right? It's not friendly in terms of computation. So even though it gets all the hype, right? People always mention correlation. And you should know the reason why, right? Why do people always go for correlation? The reason simple is scale independent, right? Whatever the scale for X and Y is, it's always between -1 and 1. So it's a nice measurement. I don't deny that. It's a nice measurement. It's a nice measurement. But if you do math quite often, you care that the calculation works, because you can always, right, scale it down by the standard deviation, whatever. But if you somehow pay attention and you work with a correlation directly, you will be in a lot of pain because the structure doesn't interact nicely with other operations, right? So covariance, from that point of view, is a much nicer structure to use. It's just the measurement is scale dependent, so you need to scale it down if you really want to make sure that, right, you can compare apples to apples and blah blah blah. The reason why, right, correlation between -1 and 1, which, notice, right, implies something like this: variance of X times variance of Y, right, minus of this. You know what implies that? Covariance square, right? It's less than or equal to variance of X times variance of Y, right? Like that. Okay. The reason is, actually, this is one of the particular case of something called the Cauchy-Schwarz inequality, which Cauchy-Schwarz is a special case of something called the Holder inequality, right? Blah blah blah. But it's a branch of, let's say, analysis, whatever. So, but you can look at into the proof of Cauchy-Schwarz inequality if you care to know that. But that's so the reason why it's between -1 and 1. Okay. So all let's say correlation is the topic you will use, or the thing you will use in statistics. If you do probabilities, covariance, right, probably you will have to interact with more. So that's covariance and correlation. Now, well, where does this whole thing factor in? It factors in when you look at the variance of a sum, right? So as I mentioned, the formula is as follows. It will be the sum of the variance plus, right? There are two ways you can write this. One way is you can write down like that. So this, right, count all pairs, including order. So notice, because it's I not equal to j, you count ij twice, right? 1, 2, and 2, 1 gets count twice. Or if you want to count once, then you can write this. Well, you need to say I less than j. Up to you, right? I like this more because it kind of reminds me of the square expansion, right? The binomial expansion for the square. A squared plus B squared plus 2AB, right? But it's up to you. But if you look at this, right, what does this remind you of? Well, this is a variance of xi, right? Covariance of xi. So really, right, this is a not so subtle way to tell you that this is really just about the sum of all covariance. right? Notice here it's just all IJ, right? Unrestricted. And you're like, really? Well, the answer is of course, because if you look at this, the variance of the sum, right? If you remember, variance is covariance of something with itself. And then you use the bilinear property of covariance on both coordinates. You get exactly that. You understand? So in effect, I was just telling you the proof of this goes like that. Any questions? All right. So where do you use this formula, for example, right? Well, I guess it's used wherever you have to do the covariance of a sum, but let me see what's an interesting thing to show you. Right. Okay. So the textbook does this, and I think it's nice. So this is a calculation you will see in 481, but let's show you here, right? So basically, okay, what quiz are we on? Quiz 3, right? So in 481, you will deal with IID sample a lot. So let's say you have x1 up to xn, IID, okay? Independent, identically distributed with mean mu and variance sigma squared. So this is called random sample, right? The random sample from 481. You have an object called a sample mean, which I suspect a lot of you have seen. Just sum them up, take division divided by n. You also have the sample variance, which is the sum of xi minus x bar squared divided by n minus 1. All right. So sample mean, sample variance. By the way, right? One thing that I would tell 41 students right away, maybe on day one, is that these things, in contrast to what you've seen in let's say baby statistics course, whatever, these are random variables. Okay, these are random variables. Maybe obvious here, but maybe not. Meaning that, right? Especially if you have done statistics, I mean, with data, almost always, right? These are numbers. Well, they are numbers because you're looking at a specific set of data. But if you consider their behavior without data, before data is collected, right? They are random variables. Okay, and statistics always deal with this as random variables. So if they're random variables, of course, you can ask for their variance and their, let's say, expectation. Okay, so let's see if we can calculate this. All right, so variance of X bar, right, is the variance of the sum, right? I guess division by n, but that doesn't really matter. Well, so the 1 over n comes out, right, as a squared. Now, I think I should have mentioned this before, but when you have independent random variables, then you can ignore the covariance terms, right? So indeed, for independent variables, variance of the sum is the sum of variance, right? Why so? Because if you have x and y independent, which implies then that the covariance of them will be 0, right? But of course, the reverse direction is not true, right? There are counterexamples. The reason why covariance of independent variables are 0 is because it's the expectation of the product, right, minus that. But we know, right, that if two random variables are independent, then expectation of product is product expectation, right? So that's why when you have independent random variables, the sum, right, you can just do that. And of course, each of them is sigma square. So 1 over n square, n sigma square. So it's sigma square over n, right? Any question? So here maybe is a place that we can advertise for a result that we'll discuss on Monday, okay? At the latest next Wednesday. Expectation X bar is what? Expectation of X bar is, right? It's not asked for here, but it's this expectation of the sum, right? Divided by n, which is 1 over n expectation of sum. But the sum, right, you can pass inside, right? Each of the term is mu. So you got 1 over n times n mu, so that's mu. So what you're looking at, right, is a random variable, right, X bar, right? The sample average has constant expectation. Doesn't matter what the sample size is, but its variance shrinks, right? It's decaying like 1 over n as sample size gets large. In fact, right, this goes to 0 as n goes to infinity, right? And I'm not sure we mentioned this, but if we have a random variable that with 0 variance, what's the conclusion?
It's a constant.
Correct. So here, right, you have a random variable whose variance is converging to a constant, right? Converging to 0. It's not exactly 0, but converging to 0. Whose expectation is this? Therefore, right, this is actually just say a hint of a large number, which says that the sample average will converge to the population mean as n goes to infinity. This is exactly a large number. And it's sort of like the basis of how we can do statistics, right? It's not too much to say that without it, statistics won't work, right? But so that's that. Okay. We'll talk about large number and central limit theorem next week. All right, any question? All right, so what about expectation of the sample average, sample variance? So expectation of the sample variance will be expectation of sum of xi minus x bar squared over n minus 1. So this is an interesting expression to look at, right? So first of all, of course, it's 1 over n minus 1, right? Expectation of the sum of xi minus x bar squared. And well, if you have nothing better to do, you can just pass the sum in, pass the expectation inside, right? See what happens. And again, if you have nothing better to do, you might as well open up this square to see what happens. Right. And what do we know? So this is the expectation of xi squared minus 2xi x bar, right? 1 second. Let me see here. What can we do? So here, right, there's some thing we want to pay attention to because we don't want to just blindly go in and do this. Notice that there's some structure going on here, right? And so, you know what? Hold on. I might want to keep the expectation outside first. Okay, so I'm just kind of working with the sum here. The reason is as follows, right? So a sum of xi squared, whatever. But here, right, x bar is a constant in terms of the sum because this is sum over I. Right. What I'm trying to say is, right, if as far as this sum is concerned, right, ignore the first term. If I just look at xi x bar, right, 2, right, and then plus the sum, right, like this, right, that's what I'm looking at. Again, ignoring this term. Then x bar is a constant, right, it can come out. In other words, this is minus 2 x bar sum over I equals 1 to n xi, right? And this, of course, right, is just n x bar square because, you know, this is constant in terms of I. But the sum of xi here, right, is really n times x bar, right? Because x bar is a sample average. So this is 2n x bar squared. Do you understand? So basically, right, this sum right here is the sum over this minus n x bar squared. Which means like that. Right? And now I can pass the expectation inside. And, you know, because the xi are IID, all the sum, right? Well, you know what? Let me just do it slow. The sum expectation of xi squared, and then minus n expectation of x bar squared. Right. Expectation of xi squared will be variance of xi plus expectation square of xi. So which is sigma squared plus mu squared. Expectation of x bar squared will be variance of x bar, which is sigma squared over n, right? We calculate above. Plus expectation of x bar square of x bar, which is mu squared. Okay, so far? Any question about the substitution or any of the steps here?
Professor, 1 over n minus 1
Yeah.
became 1 over n for n large.
No. There's no n large here. I'm just dropping the minus one
Okay. Got it.
out of carelessness. Yeah, because exactly it will be n minus one inside here. So yeah, thank you. No, so I was discussing n large in the context of x bar. And of course, there's n large for the sample variance as well. But here I'm just interested in exact calculation. Yeah, so I just drop it out of carelessness. All right, so time to collect stuff, right? So this is, this is n mu square, right? Minus n mu square. So the mu square drop out. You have n sigma square minus sigma square. So that's n minus 1 sigma square. Which is, of course, sigma square. And so what it says is expectation of the sample variance is the population variance. All right, any question? So again, right, never mind the actual result. You'll see that again in 4A1 in statistics, and maybe you will have to memorize there. Here, I just want to demonstrate, right, how expectation, right, and variance interacts with some stuff like that, right? We'll have one more example to show you. But here, the point is to demonstrate the operation and how it works with a sum. And of course, you see, last but not least, one thing that's left unsaid about the sum is that there's some sum techniques that you should know, right? When you deal with expectation and stuff like that with sum, it has nothing to do with the property of expectation or property of expectation of variance of the sum. It has to do with the techniques of the sum itself. If you cannot simplify these things and make them into some recognizable quantity, right, then you'll be into a nightmare trying to chase the interaction between xi and x bar, right? So something like that is worth mentioning. Okay, so last problem of the day, quiz 4, right? This is also a well-known result in 4A1 in statistics. So if you have x1, xn, IID, mean mu, variance sigma squared, show that covariance of xi minus x bar and x bar is equal to 0. All right, so first of all, right, this is a very important result in whatever branch of thing you do these days, right? It has to do with probability. What does it say? It says that the sample average and the data, let's say, subtract out the sample average. So some sort of normalized data. The normalized data, I mean, normalized is probably not the centered data, right? Because normalized will involve dividing by standard deviation, right? The center data and the sample average itself are uncorrelated, which is quite useful, right? Quite good. Because, again, right, it's one of those surprising facts of life that when you see interaction like this, whatever that means, right? When you see something in common, you sort of don't expect them to have zero correlation, but they do. Okay. And more importantly, even if you throw in the word normal, which is not here, then normal have a very, it's more like multivariate normal. It has a beautiful property that covariance equal to zero in multivariate normal implies independence. Okay. But of course, you require multivariate normal. But anyway, right. So this is a very nice result and good result to have in many contexts. But how to show this? First of all, you see how to show this require you to know that covariance is a bilinear operator, meaning that you can split up like this. Again, right, if you just try to change expectation or definition, it will be very nasty, like this. And second, right, this will be covariance of xi and sum of x, let's say k over n. And then this, of course, is just variance of x bar. And now you use bilinear operation again. But you see, this is a sum over all k of covariance of xi and xk over n. And variance x bar is, of course, is sigma squared over n, right? We calculate above. Now, what happens here? Notice that xi is an IID. So if k is not equal to I, covariance xi and xk are is zero, right? Are zero, because they're independent. So the only thing that survives is when I equals to k, or k equals to I, which becomes a variance of xi, which is sigma squared over n. There you go. Again, right, notice how this proof strongly depends on, you know, the bilinear operator, right, bilinear property of the covariance. I mean, not strongly relies on, but without it, right, you have a, let's say, a painful time going through it. Any question? All right. So actually, I think we still have some time, right? Let me, in the last 5 minutes or so, show you. Let X be a hypergeometric, right? Find the variance of X using the sum technique. So if you remember, right, again, you have an urn, right, that has n balls total. What was it? M plus M of them, right, is white. And N minus M is not white, so black. And you sample, right, N without replacement, right? And X is the number of whites, right, in the sample, right? So remember, right, we break X down into Xi, where Xi is 1, right, if the ith ball is white, 0 otherwise, right? And so it's this thing right here that we want to now find the variance. So the variance, right, will rely on, so if you remember, when I looked at the hypergeometric, I said the formula is not super inspirational, it's not super easy to remember, right? So the expectation is easy to remember because it's going to be sample size times success probability. Variance is not so, right? The reason is because variance has the interaction terms built into it, right? Variance will be the sum of the variances plus twice the sum of the covariance. Now, what's the variance of xi? If you remember, right, if xi is a Bernoulli, then the variance of the xi is p times 1 minus p. Right, where p is a probability of success. So a success here is having the ith ball being white. So that's going to be m over n times 1 minus m over n. Right? So the first part here is just n times m over n, 1 minus m over n. What about the second part? The second part is way more fun because the covariance term here, right, xi and xj are not independent. So covariance of xi, xj, right, is expectation of xi, xj minus expectation of xi times expectation of xj. So these two guys are m over n. So this term is m over n squared. Easy. What about this? Now, if you have looked at, logic or whatever before, you see that if you have indicator function and you multiply them, you will get something like an indicator function of the joint, the end. So it will be 1 if I and j are white and 0 otherwise. So the expectation of a product here, right, will just be the probability that you get the both I and j to be white, which is what? Well, we can do conditioning, right? Basically, first, the I must be white, and then, right, the j must be white. Condition y I must be white, which is m minus 1 over n minus 1. Sorry, this is squared here. Okay, so far? And so, every ij has the same covariance like this. So there are n choose 2 pairs. So this will be plus 2, n choose 2 times this lovely thing that we write down. M minus 1 over n minus 1 minus m over n squared. So that's the variance of hypergeometric. Notice, right, it's not exactly the expression in a textbook for the variance of a hypergeometric. Why? Because they would go ahead and clean up this formula some more, right, to give you a nice expression. But the essence of the calculation is here. You see that I would claim, and if you do this calculation, this type of calculation enough, you see that this is much easier to deal with than to deal with the formula using the combinatorics that the textbook does, right? So this is an application of using the variance of the sum, right, to find the variance of a random variable. All right, so I think we're right on time. So let's continue next Monday.
Professor, I had a unrelated to 477 question.
Yeah.
I don't know if you remember earlier, I emailed you about taking 621. And then like over the summer, Professor Winston told me that there's like a new undergrad classes coming out for math finance, and 485 is a prereq for them. But 485 doesn't fit in my schedule due to my work schedule. Is 621 enough to get into like 490, 489?
Yes and no. It depends, because the way 621, if it's run, okay, right now the state of that class is unknown because there are not enough students enrolled in that class. But if it is run, the way it's traditionally taught is that it tends to focus more on discrete models, and it leaves the continuous models and Brownian motion and Ito calculus for 622. But in 485, both will be covered, less in depth, right? Because 485 aims to give an overall exposure to everything without going into in depth. The reason we have 621, 622 is that we can go in depth into a lot of topics in each of the things. So I would imagine that 621 is not a good sub for 485 in terms of exposure, right? Because so in that sense, if the two other certificate classes require, like let's say Brownian motion and Ito calculus, then you will not see it in 621. Depends on how it's taught, right? So and then of course there's this real possibility it's not going to be offered anyway. So there's that.
Okay.
So yeah.
All right.
You can talk to
good.
Professor Weston to see how she thinks of the prerequisites, right, for those two courses would be, because I think one of them will be taught by her. So she would.
I think she said 490s by her.
Yeah, but she will be able to tell you like the topics that she thinks are necessary, right? And I think maybe Ito calculus and Brownian motion might be on the list. But if it is, then the chance you see it in 621 is slimmer than in 485.
Okay, that sounds good.
Yeah.
Thank you for letting me know.
Okay.
Appreciate it.
Sure. Cool.
Okay.
Thanks.